The interactive modules contains a number of simulators which you can use to simulate a system and perform parametric studies. I want to walk you through a particular one. It's called the Equilibrium Combustion Simulator, or interactive. Again, it should have the familiar tabs. Here is relevant animation explaining an overall reaction, elementary steps, etc. Hands-on examples and a discussion tab for your comments. And click here to launch the interactive. Well, it looks a very complex looking interactive, so let me just go over a few things. First, you will see a couple of tabs here. The first two are very important. One is where you know the exit temperature, the product's temperature. Here's a combustion chamber diagram, and the exit is right here. In this case, the exit temperature is assigned as 2000 Kelvin. On the other hand, so all the calculations are based on, you know, the pressure inside the combustion chamber and the temperature at the exit. Of course, the inlet temperature is supplied here. And on this tab, it's assumed that the heat transfer is known, which is 0. In this case, you can of course set something else. So here, the unknown is the exit temperature, whereas heat transfer is known. Whereas in this tab, the exit temperature is known, product's temperature is known, and the unknown is the heat transfer. Well, first let me describe this combustion chamber a little bit. The fuel comes through the central pipe, and the oxidizer, which is a mixture of oxygen and nitrogen, enters here, and they come in, you know, these are called primary and secondary air. They come here around the fuel, and a fire is made. A flame is burning here. So these details are not important in thermodynamics. In the energetics, in our analysis, we know the conditions of the oxidizer and fuel that are entering here, and we would like to know what's going on in the products. And what happens in between, we really cannot address in thermodynamics. There's a special branch called kinetics and fluid mechanics. Those equations have to be solved to know the details inside. But what thermodynamics can offer us, input, output, or inlet, exit states, that's plenty, and that are used to validate all other more sophisticated model. Okay, so let's try to simplify the picture. We'll do it with an example. Suppose we are burning methane with air, and we'd like to know the heating value. What is heating value? It is when you burn 1 kg of methane, how much energy is released, how many million joules. We already know the answers. It is about 50 million joules. As a matter of fact, you can go to the property tables and take a look at the heating value. It's listed on a table. So to find the heating value, we first follow the instructions which are given step by step. Step 1 is select the fuel, step 2 oxidizer, etc. Step 3, you can see those steps here, but let me just walk you through it. So you select the fuel, let's say methane. Immediately we'll notice the fuel name is changed, reflected here. The fuel name you can see right here. And also you will notice that the reactant is already shown here. Also the fuel name appears methane, and by default air is the oxidizer. Oxygen plus 3.76, you know, there's the formula for air. Also, if you go down here, you will see there are two different bar or slide bar. This is where you select your oxidizer. It's right now set to air, but you can move it up and you can get more oxygen. If you move it down, you'll get less oxygen in the mixture. Air is a particular mixture of oxygen and nitrogen in that ratio of 1:3.76. Okay, let's stick to air for the time being. And this second slide bar is to make the reaction rich or lean. What right now it's at stoichiometric ratio, in the sense that it's a theoretical reaction where there is no excess air, there is no excess oxygen left or fuel left in this. So this is called theoretical reaction because there is no extra fuel or extra oxygen left after the reaction. But if a reaction is rich or lean, then of course in a lean reaction there will be more air, so oxygen will be left over, and in a rich reaction fuel will be left over. But to make the reaction complete, you have to also make sure the products are fully, carbon and hydrogen are fully oxidized. In other words, in an equilibrium reaction, all kinds of species, components may be present. These are typical combustion products. Of course, there are a huge number of more that are possible, but these are the major products in most hydrocarbon combustion. So first let's go to the complete reaction, because the heating value of a fuel is based on complete reaction. So carbon goes to CO2, hydrogen goes to H2O, as you can see, and some nitrogen will be left over because nitrogen doesn't take part in a theoretical reaction. So we have selected methane, and as you can see from here, air is selected as our oxidizer, and the products are selected here. So we are done with setting up the reaction, but in a theoretical, in calculating the heating value, the assumption is that what is heating value? When fuel and air reacts and they enter the combustion chamber at the atmospheric condition, which is 298 Kelvin, and they also leave at atmospheric temperature 298 Kelvin, standard temperature I should say, I'm sorry. The standard temperature is 298 Kelvin. Then what happens is that the amount of heat transfer that is necessary is called the heating value. I already clicked the calculate button. Actually, I hit the enter button in my keyboard. So it already calculated the heat transfer, which is negative 50 million megawatt, negative 50 megawatt. Given that the flow rate of fuel is 1 kg per second, as you can see here, 1 kg per second of fuel is flowing. So every second there must be 50 million joules of heat released. So therefore the heating value is for methane will be 50 million joules per kg. Of course, you can go and verify that if you go to a separate thermofluids window. We can just go, I'm saying we can go to the table and make sure what we got here is correct. All the heating values are listed. If you come here on the in these tables, so higher and lower heating values are given here. And as you can see for methane, we just calculate the heating value is 50 million joules. It's the lower heating value because the H2O is in the vapor form in these particular calculations. Okay, now let's go back and see what other capabilities this particular interactive offers. Let's go to the known heat transfer tab. Of course, everything is back set to the default values. Let's calculate methane. Let's choose methane again. And in this window, what we can do, we can say that we can specify heat transfer. And specifying heat transfer to be 0 means that the combustion chamber is insulated, adiabatic. And in this case, the product's temperature is called the adiabatic flame temperature. So let's find out what is the adiabatic flame temperature for complete combustion. We assume the combustion is complete. This is a theoretical reaction. And when we calculate, after we set up the equation, when you just click calculate, the temperature is 2326. And let's try to write so that we can compare it with the equilibrium temperature. And let me explain what I mean by that. In this particular reaction, it's a complete reaction. So oxygen, only in the products there is only CO2, H2, and nitrogen, and their amounts are specified here. So you could write the reaction based on, these are the stoichiometric coefficients. You can see 1 kilomole of CO2, 2 kilomole of H2O, and 7.52 kilomole of nitrogen are produced in this reaction when methane and air reacts in a theoretical combustion reaction. The products also, you can see in a graphical output. If you click there, it's a very simple output. It can show you the nitrogen, oxygen, and H2 amount in mole fraction as well as absolute kilomoles. Okay, so let's go back, get out of this graphical tab, and come back here, and let's understand what the equilibrium reaction means. Theoretical reaction means Well, anyone can control what goes into a reaction. I can say, I can just simply change this bar and say the reaction is linear, means supply more air. So if we supply more air, for instance, and let's, for the time being, okay, we'll go there in a second. Let's assume we still have this theoretical proportion. We are supplying air exactly at the theoretical proportion. Question is, what will the real products be? Products do not have to be, the combustion do not have to be always complete. Carbon doesn't have to always go to CO2. It may produce some CO. There could be some OH. There could be all other kind of products. All this stuff that is listed are very common in a combustion reaction. So one way to calculate what's in the product is to think of all possible products and change their amounts. And there is a function called Gibbs function, a thermodynamic quantity. When that reaches a minimum, one can show that that means an equilibrium is achieved, chemical equilibrium is achieved. So using that principle, this simulator try to minimize the Gibbs function and comes up with the species concentrations. And these are very, very accurate calculations. The numbers have been compared and almost exactly the same as the famous NASA equilibrium code. So let's see, let's say we choose equilibrium products here, typical products. You can individually select them or just click the equilibrium button. And now if we do calculate again, what are the setup here? Methane and air are entering in theoretical proportion, as you can see here, with a lambda equals 1. Lambda greater than 1 means lean combustion. Lambda less than 1 means rich combustion. And they enter at 298 Kelvin and 298 Kelvin, and it's insulated. That's why heat transfer equals 0 kilowatt, and the pressure inside the chamber is set at 100 kPa. The flow rate is 1 kg. Everything is based on 1 kg per second of fuel. 17.12 is the air fuel ratio. That means for every kg of methane, there should be 17 kg of air entering the chamber. So now if we click the calculate button, the Gibbs function of the products, possible products, are being minimized. And finally the temperature is calculated, which is 2223. And if you recall, the older temperature was 2326. So about 100 Kelvin less. And this temperature is so close to the measured temperature. When you look at a flame, next time you burn natural gas in your home, in a gas stove, the methane is the principal component of natural gas. The flame temperature that you see would be very close to 2223. That's how good these calculations are. Because all reactions do not go to equilibrium, but for combustion reactions, the temperature is so high that the reaction rates are very fast. And when things happens very fast, equilibrium happens very quickly too, because the reactions that, the driving force that are driving the reactions can quickly be executed at a high temperature compared to a low temperature environment. You can also take a look at the products. Look now, there is CO2 amount is 0.904. CO is pretty low, even though, so obviously it's not it's not a complete combustion anymore. You can see there is CO and CO2. In a complete combustion, there will be no CO, absolutely. Now, what do you think will happen? Let's do a little quick what-if study. What do you think will happen if I make the reaction a little bit richer? Just by pulling the lever up, if I move this guy up, that means richer reaction means what? There will be relatively less oxygen for every kilomole of methane. So let's move it up so you can see this goes from 2 to 1.6. Well, now we have a rich combustion. That means what? That means there is less oxygen, there is more fuel. Won't you agree? Then the CO2 amount will go down and CO amount should rise because we have the same amount of carbon and less oxygen. So therefore CO production will be favored. I mean, that's kind of common sense. And let's see if the equilibrium favors that. Again, let's write down the number 0.905, or is the carbon dioxide amount, and CO amount is really, really small, 0.00995. So if I hit the calculate button, calculation starts, and keep an eye on CO2. Look, it went down drastically to 0.52 from 0.905. So as you can see, the CO2 amount has gone down and CO amount has increased so much so that it's almost equal to CO2. If I make it even richer, go up further and calculate that, we can show that the CO2 amount will be even higher. If you click the graphical output, you can see the species, the different component in the products. On the left is are the major products, and on the right are the species, trace species. The yellow fraction is blown up here on different components. So the more exotic components you add, there may be very trace amount, but sometimes those trace amounts may be very important. Suppose there's a cancer-causing chemicals, then obviously that will play a major role. If you can do a equilibrium calculation, you can predict what all species are present in your emissions. So go ahead, play with this. It should be a fun interactive to play with, and you can learn quite a bit about combustion and chemical equilibrium.